few weeks, we're actually going to look at number of systems that people have done to get a sense of where things are, right? So because so far we covered from the textbook, and you should have a fairly decent idea of what the sensors are, what the different notions are, right? And we'll see how each one of them attack different scenarios. I tried to choose like different kinds of stuff. There's a paper on habitat monitoring for today, and volcano monitoring, and so on and so forth, where each one is slightly different, and that'll hopefully bring out different issues of energy management, scale, and all those things, right? And yeah, pass the homework assignment to the front. And so that's the idea. And turns out there were 3 different slides that people put up. As I figured I'll reuse the slides from the internet rather than make my own, right? Thanks. So essentially, this is one of the very first sensor deployments out there, right? They were trying to put sensors on this duck island off of Maine, right? The idea here is it's fairly remote, right? And these people are in Berkeley, so they're across the continent. And you want to put these things into the petrel bird's nest, right? These birds are very picky. They don't like people wandering around in the nest, right? I mean, they have like statistics on, if people spend like little bit amount of time, most of the many birds abandon their nests and go away, right? So you want to not be intrusive. You don't want to go there every day to check them something, right? And the life sciences people who are doing this, really, I mean, from the paper, it looks like they actually know what they're doing, right? But in reality, they have no idea what they're looking for. They want to know what conditions cause them to breed, and what is it like inside the nest, right? But they have no idea what to really expect, right? So they don't know if it's going to be, they suspect it'll be damp, but not precisely what temperature and all those things. So they're trying to learn something that they don't know what they're going to learn. So they would like to deploy these things and be able to reprogram them on the fly. So they want to build this hardware, put them inside, and learn from them, right? So it turns out they actually had a lighthouse on that island on one end, right? So they can go there in the summer or something and put this stuff. So the birds are on one side of the island, and the lighthouse on the other side. So they have to somehow put the sensor deployment here, somehow have a multi-hop network to get it off to the lighthouse, and from there they have a bunch of PCs and running Postgres and stuff, store all the stuff, and from there you satellite upload all the links. So once it gets to the lighthouse, energy is not a constraint. Satellite time is a constraint, but not so much as what you see from here, right? So they want to build this stuff and put this thing. And I think the birds nest on different, they put burrows on the ground, right? And they may choose different burrows to nest based on they don't know what. So I think they put lots of these sensors, hoping that they'll become a nest, right? So it's also possible that you put a sensor and birds didn't like it, right? They don't know why they don't like it either, so that's what they want to figure out, right? So there's a lot of stuff they don't know, and they want to put this stuff, and they built the more platform to do that, right? If you read the paper, they have lots of stuff about what kind of sensors they chose. They chose this sensor for figuring out light, this sensor for figuring out temperature, and so on and so forth. And they put it into this package, and I think I like the 3 presentations because some of them got different slides from different sources to show how the actual sensors look. And I think the first version looked like sort of like a cylinder like this big, right? They thought they had it all like glued and everything. They had this big, and they can put it inside the nest. And turned out that some of them were too big. The nests were not that, I mean, it's like very small entrance. You want it to be inconspicuous, otherwise the birds, we don't know if the birds will reject them or something. So essentially what happens is you have a set of sensors here. I think in the experiment they had like 30, 35 or something, right? And you have some sort of a base station which connects wirelessly to all this. And then you have some kind of a multi-hub to the lighthouse, right? It had like a few servers and laptops and stuff like that. So you want to collect the information from here on to here, right? And you want this to be as flexible as possible. So you have lots of sensors built into here. So you put these things, and hopefully you put this in there and go back after 9 months or so, right? I forget why they chose 9 months. It could be that that's when the grad students come back or something like that, right? Because these are driven by some other research. You have these. It's done every 9 months because after that students go out for summer vacation or something, right? So it's time to work with students, right? So what do you think of that scenario? How difficult would that be in terms of what we looked at so far? In terms of the first chapter we looked at was on the organizing the network, right? How difficult would this be to set up this network, organize itself, that you get connectivity all the time, right? Remember, you can't go back on the field. I mean, you're sitting out in California, and this is off of Maine, right? And I think this is from April to October, and it gets colder to this thing. So you don't want to go back and stuff. And I think they chose like 2 AA batteries. They wanted the battery to last for the whole year, right? They couldn't put anything else because these are put under the ground. Because so imagine they make a nest underground, like a foot underground. So you have to put these sensors into the nest site and let them stay there, right? So you couldn't use any harvest, like you put a solar panel or something, because then the solar panel will be sticking out, will be shiny, right? And that won't be a good thing, right? So I think these things were solar powered. But the sensor itself cannot be solar powered, so it has to be with the stuff, right? So would the networking be hard? Yeah.
Especially because you're burying them underground to cause a lot more interference with the signals.
I think they had to put a little
antenna sticking out.
Yeah, like a wire or something to stick out. But that brings up a point, right? So what happens if you have like things sticking out when you have birds, right? If you notice birds, they like to keep pecking on those things, right? There's an issue of where do you keep this stuff, right? So hopefully you can keep these things close enough that won't be a problem, right? I think they kind of solved it that way because you move it closer, right? And there's only 35 here. Let's assume there are 35 here when they're fully operational, and you expect some of them to die away, right? So would any of the stuff we talked about, like in terms of scalability, would that be a concern here? So which way do you expect the data flow to be? And you expect it
towards the data center.
Yeah. Do you expect stuff to go back this way?
Not very often.
What kind of a traffic do you expect to go back this way to the sensor, like from Berkeley back to the sensor?
Software updates or some kind of new way of querying?
Yeah, software updates. So I think their model was it collects all the information and sends it over here. The queries were run off of the database here, right? So they had I think three laptops and a server with the Postgres stuff. So they were running queries off of here, right? They didn't have the benefit of all the stuff that you guys looked at last week. So it's a regular server, and at this point, the data is also replicated at Berkeley, right? So once it reaches here, you're all set, right? So there's no querying these sensors. It's only, reprogramming is one of those things, right? So if you want to reprogram, you send something back. Otherwise, all they did was they measured something and then sent it on, right? And that's that, right? So in terms of networking, this ought to be fairly trivial. This is not a large scale, and so you have to worry about the duty cycle, right? You have to worry about, so if you figure that the battery has a certain amount of capacity, like 2 AA batteries, and you figure how much each one of them has to consume, how much each of the operations should consume, and you have to worry about the variability of the components, right? So if you read the paper, they talk about the variability. So the idea is, if you buy a battery which says the capacity is X, right? It's really X plus or minus Y, right? Because these are commodity components, so they're not trying to be precisely X, right? So you have to worry about what those are. And within those bounds, you do a calculation and you figure out that on a single day, I ought to be able to use Y amount of energy, right? So with that Y amount of energy, what are the different things I can do, right? So that defines how much I can do. So that means that, I have Y units per day, right? And it's a simple equation to say, using the photo detector takes X1 energy, using the temperature takes, X2 energy, or so, and so on and so forth. I have to figure out how many times I can do each one of these such that I can still meet the budget. It's a fairly trivial numerical calculation. So you program that into the system, saying you have all these components, so you're going to take this much energy. So every 2 hours or so, you make the collect the energy, collect whatever you have to collect, send it back to me. So if my calculations are right, that system will last for 9 months or whatever my target is, right? Which is what they said, right? The paper, if you read the paper, they said, we do the calculation and said, okay, you can do something like this, right? Do you expect that would be good enough? Do you think you can do those calculations like that?
Good enough in what way?
So do you think it'll last for 9 months if you do the? Yeah.
Probably not. I mean, because the temperature changes a lot, that would change. It would change the temperature of the battery chemistry, and you might.
Yeah, then you end up with stuff like that, right? All the specifications are dependent on the temperature in which you're operating, right? So you have to, it's a sort of a loop there, right? So, for example, if the temperature becomes low, your battery capacity may go down, right? We don't know what the temperature is going to, because that's why you put the stuff in there in the first place. So it's so you want to see how far you can last, kind of thing, right? So a lot of things that they didn't expect, but they kind of learned, right? And we'll see some of the pictures that were not in your paper on some of the packaging stuff too, where it went wrong. For example, they put this into this little glass cage, the modes, right? And it's supposed to seal, but they have no way of actually knowing whether it's actually properly sealed or not. I mean, they didn't design it to let them know it's properly sealed. So sometimes it won't have sealed, and they don't know that because it looks the same. And water gets in, and then the whole thing destroys. And I think once the battery leaked, and the whole, it's acid, right? I think there's acid in there. So it melted the whole sensors and stuff, right? And the sensors turned out to be much bigger than what they expected. And the batteries don't really, like you pointed out, doesn't really do what they have to do and stuff, right? There are other challenges that they don't know how to solve, which not mentioned here, which is when you put the stuff inside the burrow, right? You don't know what the birds do with that, right? They may stomp on it and they'll bury it under the ground, right? Because it's their nest and it's moist and humid and stuff. So they may throw the sensor out of the burrow, which is okay. I mean, then you can go and retrieve it. But they may bury it underneath with mud or whatever they can lay their hand on, right? Or they can sit on top of it or whatever, right? And the calibration becomes a real nightmare, right? If you read the paper, they say all the stuff is calibrated in the factory, right? But once you put them in the ground, so essentially all of them are reporting some readings, right? So you have to figure out what those mean based on how much moisture and how much dirt is in there. So the first iteration, which is what the paper talks about, they didn't get any scientific data at all, right? You won't get that feeling by reading the paper, because the paper is all like, yeah, we did this. They don't talk about how good it worked, because it didn't work, right? Because they couldn't get scientifically correlatable data, right? So you get lots of temperature reading, but you want to have some trust in them, right? And they really couldn't do that because of a lot of issues with the packaging, the technology, and all those things, right? So in some sense, this is not such a big deployment, right? In some sense, should not be that hard. They make it purposely hard by saying you can't go back there kind of stuff, but I'm saying otherwise it's just such a small deployment, right? There are a lot of problems, and some of them are fixed, but I don't really think that, all of them are fixed yet. I mean, I think these things are still a problem, right? So we can go through different slides. And I especially like the fact that different people had different pictures, and those are good. And I think I also have one presentation from one of the authors in a retreat after this, where they were more candid about what really happened. Right? So this one is from Rutgers. It basically talks about the stuff from this paper, right? And it's fairly positive. So essentially the idea here is to be able to monitor this habitat, especially in the scenario where you don't want to go back and mess with the environment, right? The birds don't really want you to come in there because these are shy birds. So you want the ability to be able to do some processing or store something so you can get it back later on, right? And the first point, they kind of got away with it because the storage happens at the lighthouse, right? The lighthouse has enough energy for lighting up the lighthouse, so they didn't have any trouble with running the laptops, or you didn't have to worry about weather either because it's inside the lighthouse, right? So it's it's a normal laptop and so on and so forth, right? You want the ability to communicate with them, right? And it turns out it was made a lot easier because you have to worry about the communication from this area, right, from the sensors to the first base station was problematic. That's one thing you have to figure out how it works. But from here to here, there's no reason why they shouldn't work. I mean, these stations were fairly tall, and they had a solar panel to collect electricity, to collect the energy and stuff, right? And the antenna was like fairly high off the ground that you shouldn't have any trouble talking from here to here to here, right? So you're only concerned about the communication at this point. I think from here there's a satellite link back, which was slow, but I'm guessing like Australian kind of speed, right? Probably a few kilobytes per second kind of thing, right? And what they really wanted to do was be able to do the power efficiency stuff, be able to predict that this thing will run for 9 months or so, right? And in a lot of sense, many of them failed, right? But few of them actually survived. So the negative part was a lot of them failed. They were not able to get meaningful scientific data, what have you. But it did, and some of them did survive and function all the way through, right? Now, you may not be able to use the data that they produce, but still, from a power efficiency perspective, some of them did get through, right? And like looking back, I think it's also, I don't think they should have stayed with like AA battery. I mean, I think they should have used more like the 9-volt battery or something which has more energy than the AA batteries, right? But anyway, they tried that one. And the main thing that they really stress is these are application-driven approaches, that you have to come up with solutions which work on these scenarios, right? You can't have a generalized solution, it has to work for this scenario, right? Do you buy that? That in these sensor scenarios that you have to have something which is application-driven, which is driven by what application you're doing. Obviously, you can't say yes or no. It always depends, right? But in general, is that a notion that you can go with, where you develop a technique for a particular sensing scenario, and that's that? What's your gut feeling? Yeah.
Seems like at this point, at least, you're going to have to be pretty application specific, because a lot of the problems have to be solved, and so you have to think about estimations and stuff that are specific to your scenario in order to get, meaningful data.
Yeah, but at the end of the paper, they say what we really need is some kind of abstraction so we can program, right? So yeah, they talk about it as a goal, but at the end of the paper, they kind of give up and say, you need a little bit more support, right? This is before tiny OS and all, I mean, that kind of support. So yeah, you would like it to be very application specific, but then the development cycle becomes longer and all those things. You need to fully understand the system, and then it becomes like a product, right? So yeah, you want it, but you also want it to be all the nice stuff, right? So yeah, so those motivation, you don't want to disturb these things. And there's also economical stuff, right? So if you're in California and this is in Maine, right, you may not want to keep flying, right? Or you may not have enough students to keep sending off to Maine, right? Because Maine in the midwinter does not sound all that exciting, especially since I think it's 15 kilometers off of another island off of Maine. So it's really out in the ocean, right? So this is not a place where you want to go when it's like really cold and stuff. So that's the experiment, the Great Duck Island. So I've seen people who are interested in finding out what these birds are doing, so they wanted to put these things. And so I'm going to go through some of them very quickly because there's like 3 different slides to look at. So some of the requirements that they had was you need to be able to access it from Berkeley, right? Because that's all the researchers are in Berkeley, so you need internet access. You needed hierarchical network. That's pretty much driven by what they have to do, right? This was there, right? Lighthouse was there. They didn't have any control over it. The birds happened to be here, right? So this was decided. This was decided. That means the only choice they have is like this link, and it pretty much, you can tell it looks like a hierarchy, right? Because you want the information to flow from here to here, and only from there here to there, right? So it naturally follows into a hierarchical model, right? So I don't think you would argue that hierarchy is a good thing. In this case, hierarchy seems so straightforward. And of course, the longevity. You want these things to last for 9 or so months because you can't go back and keep replacing them. Both because the birds don't like it, and both because you probably don't want to go all the way to the island. And some of the thing which come off of that is it's operating off the grid. So it's not going to be, so even though you have network access, you don't have complete direct control of them. You have to send it through these systems. I think the energy to program them, I think I forget what the exact numbers are, but I think it's like, if you want to program something in 5 minutes, it takes as much energy as what the sensor would take in an entire day, right? Because you have to send the data back and stuff. So you don't want to program them often because reprogramming would basically deplete the battery for the entire day, right? I'm not talking about reprogramming. I think reprogramming to send different data would take you that much energy, right? And you want to do in this to be inconspicuous, right? And I always feel like computer scientists are not really trained to be building these things and putting these things, because the packaging industry seems to be a lot ahead of what computer scientists and hardware people would do, right? So I'm sure like the people who are building all these things, building cars and stuff, know how to build remote controls which are a lot more temperature, moisture resistant than what these guys can do. And you can see some of the stuff. I'm sure if you send it to a professional engineer, they'll be like, oh no, you can't do that, right? Like for example, if you think of the iPod, right? It's fairly well said that moisture doesn't get in all that well, but it's not something that you just do it as a class project in an afternoon kind of thing. This is fairly involved and stuff. So they did some of the stuff that in hindsight looks kind of dumb, right? And you'll see some pictures of what they did, right? So what they really wanted to do was have these systems be stable and be able to get consistent data. And at this stage of the technology, they don't even know how you would achieve that, because there is no way of calibrating these things other than what the hardware itself would do. They can't send a command to say, recalibrate yourself, right? And calibration from these, when you buy these sensors off the shelf, they're designed for something, right? So if you buy a temperature monitor, right, the manufacturer probably intended it to be in a certain location, right? it's highly unlikely that you find a sensor that is designed to be put inside a damp underground bird's nest, right, with all the chicks and birds inside doing what they do and left there for months, right? Because corrosion, all those things are not necessarily what the manufacturer intended. And you don't have the budget to actually have a custom built one precisely for that. So that's the challenge. And you wanted you want some level of stuff when you're there, when you're on the island, but most of the stuff are offline. And you want the data to be archived. I think they collected over 1 million samples, right? Maybe they're not statistically they're not valid as a science experiment, but they collected a whole bunch of data so that they can go back and look at the stuff, right? I haven't heard back on what they actually learned, right? So to give a sense, there's another project which is trying to figure out how tides act on Oregon coast. Right? So they want to put lots of cameras and sensors. I think we'll read one of the papers later on in the class. Along the Oregon coast, I think like 1,300 miles. And they want to figure out how the tidal surge works, right? So essentially, I think the tidal surge, the water kind of goes up from whichever direction, right? So essentially, if you look across the whole coast, some water rises and some water may fall, kind of thing, right? But it's a very small phenomenon. It's not like, water's here and then there's like a step kind of going. So across miles, it kind of slowly raises. And the way they've done that before is to send a graduate student, sit by the beach, and measure how these things happen, right? So these things happen in snail space kind of stuff, right? So they can collect lots of data, right? But to look at the data to try to make sense of what is happening, right? It's not a trivial task. Mostly because the people who it should make sense of, they have no idea what they're looking at, right? They're used to sending a grad student who sits there and says, okay, at 2 o'clock, the water is like 2 feet. At 8 o'clock, it's 4 feet or something, right? So they know that at 2 o'clock, at 2 o'clock, the water was like, let's say here and was here. They're used to this one, right? So if you have a sensor which gives you readings like this, right? Right? They're much happier with these 2-1, and then they can kind of assume it kind of went like this, right? But when you send like this, and if you have like very high fidelity sensor, it might turn out that it's actually doing every wave, it's showing like this, right? So you see some kind of so if you do all this stuff and give it to them, right? Frequently they say, okay, I'm just going to use this and this data. I'm going to ignore all the stuff because we don't know how. We've never seen something this fine, right? And some of them may be happening here because you're not looking at the data yourself. You're giving it to somebody. So you can say, I collected million entries, but it's the life sciences people who are trying to figure out what that means, right? So they have to look at this and go like, there's a bird sitting on right top of the sensor. That's why it's like 100°F in the middle of winter, because the mother is actually sitting on the sensor or something. But that sort of a thing, right? So hopefully the data mining and stuff can be done offline without actually sitting there and trying to figure out, right? I think there are some graphs in this picture which look pretty, but yeah. So essentially that's the service they had. Over on the top you have the sensor, right? I think they only put one patch up there, connects to this network over here to the base station, and from there it goes on the internet back to Berkeley. Right? And these are, like what you want. These are small, robust, inexpensive sensors that you want to deploy. And as they were doing this, they were building those sensors. So if you look at the mode they had in the picture, this is the first generation. It's fairly bulky and fairly big and fairly non-compact. Right? So at this stage, they actually had like two pane. There's the sensor, and then you have the computational part. So you could actually sandwich these things on top of each other. So you can change what sensor you want, right? This goes more into the hardware. How do you build the hardware to get the solutions that you want? And basically, we talked about some of this stuff. So I'm going to skip through this stuff. Basically they talk about what kind of hardware they had, what's the architecture they looked at, and here's the equations on each of the operations, how much energy you take. So hopefully you sit there and you figure out how much each of the operations would take, and you figure out what's the budget you can have per day based on what the battery you have, and then you kind of come up with a schedule that is possible, right? So if the schedule is too aggressive, then you'll drain the battery. If it's too non-aggressive, then you could have done more than what you actually could, right? And yeah, so they had these things were running this 802.11b using Surf-Cube, which is sort of like your crossbow-based star gauge, right? So essentially getting the data out. And at this here, they're running a Postgres, which is a regular database. So this is a regular database, and so you stored the timestamp of when the data was collected. You also stored, I think, the temperature of the different components for debugging purposes, right? Including the one inside the lighthouse, right? And yeah, so these are some of the graphs, right? So I've seen those graphs put up by this team. This is a very strong team, right? They were one of the first ones to do this stuff. So they have graphs like these, right? So this is a thermophile data. I guess that's the temperature on the y-axis and the data on the x-axis, right? So the next challenge is to figure out what that means. Not to us, but the people who are studying these petrels, right? So they have to look at this, and then hopefully they'll understand what's going on, right? Hopefully they'll say, okay, like when you see this little notch here, that's interesting. So they're trying to figure out, they're trying to answer stuff like, for petrels to find a nest, the nest has to be this moist, or like, the temperature has to be something. It should be dark or something like that, right? So they're trying to correlate this to figure out what might be happening in that nest that the birds tended to like, right? So that's all I liked about this particular paper, right? Yeah, this one, this is from Ohio State. And this one went a little bit further in terms of more pictures and stuff. And it's still talking about the same paper, but they had more pictures, so I figured we'll look at that one. This work was funded by Intel, right? Intel was a major funder through Intel Research Lab. And the reason was Intel wanted to do this inside their own manufacturing plant. They were very interested in automating the manufacturing plant, putting sensors and be able to control different components within the plant. So they're funding a whole bunch of these things, right? So it kind of seems counterintuitive, but they have similar concerns that they don't want human beings to be going inside their ultra pure labs, right? So the more they can avoid sending human beings and the more things can kind of fix themselves, the better it is for them, right? So now those are the little birds, and they don't like to be touched. They don't like to be acted on. So you have a picture of somebody holding that bird, right? So they're fairly picky, and you want to see study things about these birds, and they're very shy and stuff. And some of the data sounds very horrible. I think if there's very small number, like you see them for like 10 minutes or something, then 20% of the birds of the eggs don't hatch or something, like some drastic number, right? And that's the I guess the chick sitting in there. And so you want to deploy these things, and then hopefully you'll get all the results, right? I haven't seen anything which showed that they actually succeeded in that one, right? That the birds didn't bother with their stuff. So that's the duck island. And yeah, so this is the lighthouse. I don't know if somebody actually lived there all the time, but there's a lighthouse in the house, and this is their base. This is the stuff which is here. Like you can see a couple of laptops, and I think they had a server too. And those ones are that's the access point. I don't know if you can see in your picture or something, but you basically see a Yagi antenna pointing. This is a Yagi antenna, and there's like this tall antenna. So there's one antenna which is like this tall, and then there's one antenna which is sticking out this way. And so these things are the ones over here. They're big. They have enough energy. So energy is not really a concern for these, right? I think they had other concerns. The wind was blowing them a certain way, and the antennas had to be a certain way and stuff. But these are fairly big. So then you had the deployments. You had to, again, if you can look here, like these are the modes, right? You kind of put them inside the thing. So this little black thing is the mode, and you want to put them across the thing, and you want some of them to be hidden by rocks and stuff. So you just leave them there, right? Okay, so whatever they put under the rock is where they got the temperature stuff. Animations. Okay, so the way it operated, within these networks, right? As the simulation was showing, they basically form an overlay, send the packets over to the gateway, right? And you have another patch which does the same with the gateway, and goes through this transit area to get to the base station, right? And from there, it's fairly standard. Yeah, so this is the first generation sensor nodes they had. So that's the computational component with the two AA batteries under the stuff. And this is one of the sensor stuff. So you can find the right sensor and kind of attach it to the computational stuff. So this little connector is supposed to be able to connect many of these to get more sensing capabilities, right? So essentially, those are the sizes and stuff, and they discuss some of the sensors that they use. So you put them inside these containers, right? And these are clay containers and you put the modes inside, and with enough holes where you can get the temperature out. So you still want it to have enough way to reach the environment. You don't want it to be so insulated that all it's measuring is its own temperature, right? But still not be affected by these things, right? And those are some of the stuff. So you have two AA batteries, and you figure out how much energy that those batteries can deliver to you, and then you figure out what that translates into for over 9 months. So if you assume this much battery capacity, you figure out how much you get per day, right? Based on equations that are probably not validated, like what you pointed out, right? Because these are commodity batteries, so the manufacturers are not giving you perfect information, right? It's also you're assuming that if you have a capacity of 2200, right, that you can deplete it like this, right? That if you linearly deplete it, and this is 9 months, right? And the rate is 8.18. If you do 8.18, you go like this, right? Batteries in real life may operate like this, right? They may drain faster or slower depending on. Actually, no, it may like this, right? Initially, when they have enough energy, they probably go go better, and then towards the end they just drain quickly, right? So, but you do those calculations and you figure out how much of each component should take and how much variation each one of them should have, and based on that you figure out what's the duty cycle, right? For example, if you have sampled all sensors, operation 21 minutes, the duty cycle is 1.45%, meaning you can do 630 samples per day, right? So you figure out what's the sample rate and send it off, right? And you also, at some point, after you deploy this, you realize that there's no action. I think one of the stuff they mentioned is during the daytime, the birds don't go into the nest, right? So you can turn off these sensors during the daytime because the nests are empty, and the birds only come in later in the day. So they can program that later on. If they don't see any temperature at all during the day, so they can wait till the night. So essentially, then you have to create the schedule of when they need to communicate with each other, so to send the data back, right? It's a fairly simple operation here because you have each of the sensors, each of the nodes have all the sensors that you want, right? You set some schedule of what they have to do, and they wake up, they forward the information over, right? So the schedule would be something here has to wake up so often, send it to here, and something here would have to wake up so often, receive this packet, create its own stuff, send it back over and stuff. And once they had finished all the operations, they all go to sleep, right? And that's that, right? So if you want to reprogram them, you have to reprogram them at the interval that is predestined, where they all would listen for something. And the one nice thing about this case is when they put the sensor to begin with, they can put them in a good position, right? So for example, in the case of, you don't want to put them under a rock if that turns out not to be good for wireless stuff. So these are not thrown in there, these are placed in good locations. They can measure the signal to figure out what's the best location. Now the birds can of course move those things, and then all bets are off, but at least before you can do that, right? Yeah, and after you do the stuff, you can change what they do, because like stuff like daytime, nighttime, or some of the sensors don't work, you can turn them off, kind of thing. Right? I guess here's that data again, right? Actually, they have interpretation that this means that the petrel left on these days. So I guess when it's like this, that means the bird left. Right? So on 21, 23. Okay, so bird left from this time to this time, and here to here. I don't know what this is, right? Half a bird came back. Right? But anyway, so you can look at this stuff, right? And if all you find is the birds actually left on these days, right? Then from the science perspective, they would just be happy if you have a sensor which only gave that information, right? It only sensed once a day and basically said if the bird is there or not, right? All these variations may or may not make sense to you, right? But these are computer science folks who want to build this as a cool toy, not the life science people, right? And so one of the things that they want to add was to figure out how these things are operating. So I think they're measuring so in each of the measurement, they also add the battery voltage that they measured, right, as a way to debug. So they don't know what to look for, so they wanted to figure out what values would help us in the future for debugging, right? So one of the things you look at this stuff, right, how impressed are you with what they're trying to do? Based on what you know about other appliances in your home, right? How many sensors do you carry around? Not networked, but generally sensors, right? That you use, which communicate. Maybe it's network, but not necessarily like this, right? How many of them can you think in your home? Like for example, this one, right? This is sort of like that, right? This one has a little infrared here. I mean, it's not sensor, it doesn't do any computation or something, but it, in some sense, it senses whether I'm pressing up or down. and it communicates with that one, right? It has a little battery inside, right? So whoever designed this would have had to worry about some of this stuff, right? They wouldn't have to worry about me putting it inside water, but they had to worry about me putting like chalk dust and all those dust and everything. They had to worry about how long the batteries last and stuff, right? Not to the extent that they worry about, but still to some extent, right? And TV remotes and a whole bunch of those stuff, right? Do you think that if those folks were designing this stuff, they would find this interesting or to look at, or this stuff would sound sort of boring? What's the impression of this stuff, right? This is not that far back, so this is like, what, 6 years back, right? Yeah.
It doesn't really seem that complicated. I mean, cell phones and everything always, works battery lifetime, but PDAs, you can write programs to query the battery. I mean, it seems kind of basic. It seems people that, design remote control stuff, maybe kind of laugh because you don't want to replace your TV battery every day, so the same thing, pretty much.
But remember, these projects were funded with lots of money, right? These were funded by DARPA and stuff, right? So they were trying to do some things, and they have an opposing view, like knowing what you have known so far, right? Yeah.
The trick here is if the battery does die, you've lost it. You can't get it back. There's not somebody there to just change the battery, put a new one in, and also everything has to be done autonomously. So that thing obviously doesn't have to turn on until you press the button. On these ones, it has to be something where it's predefined, measure at this time, and then transmit your data at this time. It's the interconnection of a lot of simple parts into something a lot more complex.
Yeah.
Like a temperature sensor isn't that complex. When you're sensing the temperature in a damp area and you need to transmit that back and calibrate your sensors without somebody actually being there knowing what the real temperature is.
Yeah. I think there's a mixture of both of those, right? And some of the times, a lot of things that you think ought to be done was never done, right? I think one of the projects from here, which I don't know too much details, is monitoring the sewage system in South Bend, right? So they have sensors built inside the South Bend sewage system, and they go through some of this stuff. And obviously, they have hire more industrial folks who know how to put sensors inside sewage, because I have no idea how things work in sewage, right? But so they don't know those components, but still a lot of them are unknown, right? So it's a mixture of stuff, but it's kind of like weird when you look at the reality of what you could do and what you would like to talk about from the book perspective. You talk about millions and stuff, and you're kind of stuck with these little ones and something which seem like you should be able to do it off the shelf and get it done with. Sometimes it turns out to be pretty hard, right? You seem intense, sorry. So that's what this one had. Actually, so the last one was from these guys itself, like a year afterwards, right? So it's more. I mean, this was after the paper. This paper was published, so they had time to figure out what went wrong and stuff, right? So again, I mean, of course, they have the same stuff, right? So why this is interesting is the same, right? And this slide we've seen before, and yeah. So essentially, they have a couple of like a satellite router, a couple of laptops in the lighthouse, right? Like over here. They have a pause strip to reboot this machine, right? So essentially, that you send a command, it reboots it toggles a pause switch, so you can reboot those machines. And they also had like a camera added here from a different project. So now you're trying to figure out what really happened, right? So if when it notes that the temperature of the burrow kind of changed, right? So if you want to say that the bird left at that time, like on one day it looks like it was like 3/4, right? So it's either the bird was too cold or like something was happening, right? So you want to look at some other camera to see what really was happening at that time. So they had a camera that could be programmed to zoom into some location to see what's really happening, right? And yeah, so these are some of the problems that they observed, right? The first one is the modes are too big, right? It was too big for a whole bunch of stuff, and it was like it was too big, and they didn't realize it till they actually went there, and then of course they couldn't do anything. So they tried to put it where they could, and the packaging did not really work, right? Because when you turn it from lab to reality, it didn't actually work. Yeah, the nodes, they lost a sufficiently high number of nodes, and the data they collected was not scientifically meaningful, right? Because in part, the science people did not know what they wanted to look at, and in part, even if you gave them the data that they asked for, they have no idea what to make of it, right? Because they have no basis to look at this stuff. So it helps them in the larger scheme. So if they notice that something happened, then they can look at the data and say, okay, I noticed this was happening, so maybe this is a correlated kind of stuff. But these are not like earth-shattering from their perspective. Like, this is not leading them to publish papers like crazy. For them it's the same. So that's that. And that's actually true for a lot of these deployments. A lot of these things that you have good data and stuff doesn't really work out for the other side, and you want to fix with that. And they had some problem with the power conversion, some stuff. Right? So obviously they took this into heart, and they built the next generation of sensors. So this was the ones that they had initially. And the newer sensors were like those, like the white ones, right? And the white ones were better packaged and better organized, so it's not so bad, right? Some details on how the packaging and all really worked, right? So they now have a new battery, lithium thionyl chloride. So yeah, so they had to. I mean, the software was one of the biggest lessons that they learned. They would like it to be like we talked about, not general purpose, but you still like some abstraction because somebody has to program them, and you want them to be a little bit more useful than completely for this system, right? So they had 26 burrow modes deployed and 12 weather stations, the forwarding nodes, and so they were replicating all the data that they were monitoring back at Berkeley, and they had these overview cameras, right, which is not part of the system, but they are permanently connected. They're collecting pictures from the lighthouse, so they can figure out what is happening, right? Some way of knowing what really happened, because essentially, if you want to leave it for 9 months and then come back and you plot the results, you want to know what really caused each of the different stuff, right? Yeah, they had like a video logging, but from the camera, but then you have to synchronize the time from that with the sensors, because these are two different systems. So I don't know what these graphs are, right? But these look like there's a bunch of sensors at different locations. And actually, okay, these are the locations. These are burrow mode locations. And this is a percentage of packets received from each mode. I'm not sure if you can see them, but these are the repeaters. And the numbers are higher here, right? 80 something, it's like 50, and then it's 34, 41%, and this one is higher. This is 85, and this is 34, and this is 52. For some reason, this is more. It sends more data than these two, right? Yeah. So these are this is the temperature reading from different boroughs. Each of the color 209, 210, 210, like this, right? So 209 is 209 is here. 209 is here. 210 is here. So essentially, these two sensors are right here next to the repeater, and 209 is the blue, and 210 is, I think, green. So that's the temperature over that duration, right? So some sensors have action, and some sensor has, the 202 seems to have lots going on. What you really want is be able to plot in this graph, right? But each one has an error by itself, so you want to make sure that they are comparable, right? And that's a big challenge, because at this stage they were not doing any calibration on the site. So even though temperature may be saying it's 10 degrees, it could be off by a few degrees, right? And this is the humidity from the boroughs. It seems like these days were dry and hot, right? On this one, it's dry and hot. And hopefully the people would know what that means. And the passive IR reading showed that something was happening on that day. I don't know what was happening on that day. Maybe the bird was there or not there, whatever. These are the weather stations. The same for number of packets received and humidity readings. I have no idea what happens like here. There seems to be a gap here. But so essentially, this is what you want to get. You want to get lots of these graphs, right? And whole bunch of these graphs. And the next stage would be to make sense out of them. Making sense out of them would mean that you can, from a computer science perspective, say something about the validity of the results, and then from the life science perspective, make some sense out of them, right? They're looking for long-term kind of concepts, right? Yeah, so one of the packaging stuff that they ran into, if you look over here, I don't know if you can see from there, but essentially the battery leaked, and it ate through the whole modes, right? So they had to figure out that you have to isolate the battery leaks from the rest of the system, right? And yeah, for the battery venting, that's not sulfuric acid, right? H2SO4, SO3. SO3 sulfuric acid?
It's sulfurous acid.
Sorry?
It's SO3, it's sulfurous.
Sulfurous acid.
Yeah, it's different.
Yeah, that's sulfuric is 4, right?
Yeah.
Okay, so some acid, right? Yeah, they forgot to tell how it's well packaged. I mean, stuff like that. I think if you talk to consumer goods manufacturers, they'll tell you, right? Because they deal with that all the time, right? So when you put the battery in, you want some indication that some snapping noise kind of stuff, which they were not experienced, so they didn't do that. So some of them, they thought it was like well glued. Turns out they were not. So but majority of them survived the severe weather. So that's good. So the other stuff you don't know is whether they create something with the environment, right? Like they create, once you're using these little batteries, they may be creating enough heat that the sensors pick up their own heat kind of stuff, right? Or he warm up the burrow, right? it shouldn't happen, but you want to make sure that those effects are not happening. Right? So I mean, they went on to do a little more. I think the site is now long since gone, right? I think they did that for a year or so. And like with most of the academic projects, the funding probably ran out, students probably graduated. And so from the life science perspective, they may not have learned anything because, people kind of moved on kind of stuff, right? This is the example of like these things. And there are a lot of projects which try to do this. So essentially what happens is, if you are a faculty and you want to do this project, you find something which is near you, which is interesting, right? So if you live near a forest, you do forest monitoring. So there are projects on forest monitoring. If you live near a lake, you do lake monitoring or whatever, right? So you define something that's easy to do. And so these are the range of stuff that people talk about. And one of the themes that you notice in many of these systems is the scale is usually not that great, right? Because you're not fighting a war or something. You want to deploy a few sensors, and usually you have control over where to put them. You don't just throw them, and you want them to run for a long time, right? And that's the main thing you want to look at. And you kind of know what kind of things you would want to look at, like temperature and moisture and all those things, and you measure them, right? There's another project which is looking at the moisture around redwood trees. So they wanted to see how the moisture on redwood trees is like 150 meters, right, tall. How it, so they put like sensors every so much height, and you want to measure them for a year or so, right? And you go from there. Right? So within Notre Dame, how many of you are working on something similar to this model? Actually, those guys are not here, but Team Track won't follow under this model, right? It's more mobile and stuff. So we were doing something like this from the geology department, trying to put it on the lake. I have no idea what happened to that. They wanted to see what's the salinity and all those things on the St. Joseph River or our own lake. Right. Yeah, so that's all I have. So I want you to think these things in the context of what we did from the textbook. And the textbook was fairly general, right? So the idea is we'll go through these systems to get a sense of what people have to worry about and what they are talking about and stuff. And so do you have any questions, or how's the project coming along? Project report is due, but have you guys been talking about beyond the project report, doing the work and stuff like that? Okay. And if you need any hardware support or something, let me know, because it takes a while to get this stuff. Right? So there's nothing, I guess we'll leave early. Control over them, right? So the first problem that they talk about is to try to figure out the clock phase difference, right? Which is trying to figure out there's a clock here, there's a clock here. We want to figure out right. So suppose these are two clocks like this. You're trying to figure out how much phase they're off, right? They're still ticking at the same time, right? So the way that you do that is you have a node, right? This node is operating at time t1, right? This node sends a message here with the message with the time t1, the local time, into the message and sends it across, right? So when it receives here, the time it receives is t2, right? And t2 essentially is t1 plus d, the delay that we don't know what it is, right? And plus the phase difference, right? We don't know what that is either, right? It could be plus or minus. Let's assume plus for the sake of